Welcome to World Explained. In this episode, we're looking at the semiconductor superpower raised. Why microchips are often described as the new oil? Not because chips are a fuel you burn, but because they are a foundational input for almost everything modern states care about: economic growth, technological leadership, and military capability. The competition is not only about who invents the best devices, it's about who controls the supply chain, who sets the standards, who can keep production running during crises, and who can deny critical technology to rivals. To understand the geopolitical importance of semiconductors, start with what a chip actually is. A semiconductor chip is a tiny piece of engineered material, usually silicon-etched with microscopic circuits. Those circuits process information and control electrical signals. Every time a phone takes a photo, a car manages its braking system, a data center runs AI models, or a missile guidance system navigates, semiconductors are involved. They're inside consumer electronics, medical devices, industrial machinery, satellites, telecom networks, and modern weapon systems. If chips stop flowing, economies slow down, and militaries lose access to key components. What makes chips geopolitically unique is not just their importance, but how difficult they are to make. Advanced semiconductors require extreme precision, specialized tools, and years of know-how. One modern chip can involve hundreds or even thousands of steps, and the supply chain spans many countries. That supply chain is also uneven. Some countries dominate design, others dominate manufacturing, others dominate the machinery needed to produce chips, and still others dominate raw materials or chemical inputs. This creates interdependence, but also vulnerability. In geopolitics, vulnerability often turns into leverage. A useful way to break this down is to think in layers: design, manufacturing, equipment, and packaging. On the design side, the most valuable asset is intellectual property architectures, patents, and software tools. A large share of leading chip design and electronic design automation, or EDA software, has historically come from companies based in the United States and allied countries. On the manufacturing side, the world relies heavily on a small number of foundries, companies that fabricate chips at scale, especially at the most advanced nodes. This is where Taiwan and South Korea are central, with companies like TSMC and Samsung. Intel is also a major player, historically integrated across design and manufacturing, and now emphasizing foundry services as part of a broader strategy. And there's equipment, the machines that actually build the chips. This area is dominated by a small set of suppliers, including crucial high-end lithography tools, where the most advanced systems are produced by a very limited number of firms, concentrated in allied countries. Finally, packaging and testing, once considered a lower-status part of the chain, has become strategically important because advanced packaging can significantly boost performance and enable new forms of AI hardware. So why call chips the new oil? Oil powered the 20th century: transportation, industry, and military mobility. Semiconductors power the 21st century: computing, communications, automation, and intelligent systems. But there is also a deeper analogy. Oil created geopolitics around choke points, alliances, embargoes, and strategic reserves. Semiconductors now create similar dynamics: control over critical nodes, export restrictions, strategic stockpiles, and industrial policy aimed at reducing dependence. Nowhere is this more visible than in the relationship between the United States and China. The US-China technology rivalry is not just about tariffs or trade imbalances. It's about the future of economic and military power. China is a massive market for semiconductors and has invested heavily in building domestic capacity. The United States and some allies, meanwhile, have pursued export controls designed to limit China's access to certain high-end chips and advanced manufacturing tools. The strategic logic is that cutting-edge semiconductors are enabling technologies for advanced AI, high-performance computing, and modern military systems. If a rival can be slowed down at the chip level, it can be slowed down across multiple sectors. This brings us to a key concept: choke points in the semiconductor supply chain. In oil geopolitics, choke points are narrow passages like straits and canals. In chip geopolitics, choke points are the specialized capabilities that are hard to replace, like advanced lithography equipment, top-tier foundry capacity, or critical design tools. These choke points create leverage. They also create incentives for countries to build resilience and redundancy, even if it is expensive. Taiwan sits at the center of this story. Taiwan is home to TSMC, one of the most important semiconductor manufacturers in the world. A significant share of the most advanced chips, used in flagship smartphones, high-end servers, and increasingly AI accelerators depends on Taiwanese fabrication. This creates a geopolitical paradox. The global economy benefits from concentration because it is efficient, but geopolitically it is risky because it creates a single point of failure. Any major disruption in Taiwan, whether from conflict, blockade, cyber attacks, or severe political crisis, would ripple through global supply chains. That doesn't mean the world has no alternative, but it does mean alternative capacity is limited and takes years to expand. South Korea is another pillar, with Samsung playing a major role in both memory chips and advanced logic. Memory chips like DRAM and NAND are essential for everything from phones to cloud computing. Memory is sometimes overlooked in popular discussions, but strategically it matters because modern computing depends on massive memory bandwidth and storage. South Korea's position adds another layer. Semiconductor supply is not concentrated in just one place, but it is concentrated among a few allies in East Asia, which amplifies both strategic importance and regional risk. Then there's the United States. The U.S. remains a powerhouse in chip design, advanced research, and parts of the equipment and materials ecosystem. Many of the world's most influential chip firms are American or operate heavily within the U.S. system, including major designers of CPUs, GPUs, and AI accelerators. But for many years, a large share of leading-edge fabrication capacity moved offshore, especially to Taiwan and, to a lesser extent, South Korea. The result is that the U.S. has immense influence in the brains of the chip world, but has been comparatively less dominant in the factory floor at the most advanced nodes. That imbalance became a political and strategic issue, especially after global disruptions exposed how fragile supply chains can be. Europe plays a different role. It is less dominant in mass leading-edge fabrication, but extremely important in specialized supply chain segments, including parts of the equipment ecosystem and advanced industrial technologies. In chip geopolitics, who matters is not just who makes chips, but who makes the machines that make the chips, and who supplies the specialized chemicals, optics, and precision components. Japan is also a critical player in materials, chemicals, and high-precision manufacturing equipment. And beyond the headline names, there are many smaller but vital suppliers, producers of photoresist, specialty gases, silicon wafers, and precision components. If you want to understand why semiconductors are so hard to reshore or replicate quickly, this is why. Rebuilding the supply chain is not one project. It's dozens of deeply specialized industries, each with its own talent pipeline and quality demands. So what does the race look like in practice? Governments increasingly treat semiconductors like strategic infrastructure. That means industrial policy, subsidies, tax incentives, research funding, and efforts to attract fabrication plants. It also means friendshoring, shifting supply chains toward allied or politically aligned countries to reduce dependence on rivals. And it means risk management, building redundancy, stockpiling certain components, and investing in cyber and physical security around key facilities. But this industrial policy approach raises hard trade-offs. Building a leading-edge fab is extremely expensive and takes years. The workforce demands are high. The supply of specialized engineers and technicians is limited. And because technology nodes evolve quickly, a plant that is state-of-the-art today can be behind the frontier tomorrow. That makes semiconductor strategy unusually time-sensitive. Delays are costly, and the path dependency is strong. Now, let's talk about chip diplomacy. In classic diplomacy, states use trade deals, security guarantees, or energy contracts to shape alliances. In chip diplomacy, access to semiconductors and manufacturing capacity becomes part of strategic alignment. Countries that host critical production like Taiwan and South Korea become more strategically central to allies who depend on their output. Countries that control key choke points like advanced equipment or design tools gain leverage in negotiations and coalition building. In countries that are cut off from advanced chips may deepen ties with alternative partners, invest heavily in domestic substitutes, or seek new technological pathways to bypass restrictions. Chip diplomacy also shows up in export controls. Export controls are not just about stopping a specific shipment. They're about shaping the technological trajectory of a rival. If advanced manufacturing tools and leading-edge chips are restricted, a targeted country may still produce chips, but it may struggle to stay at the frontier. That gap matters because frontier chips drive performance in AI, supercomputing, and advanced communications. However, export controls come with risks. They can accelerate a rival's push for self-sufficiency. They can encourage the creation of parallel supply chains. They can put allied companies in difficult positions if they lose access to a large market. In other words, restrictions can slow a competitor, but they can also reshape the global tech landscape in ways that are hard to predict. Another key topic is the difference between leading-edge and legacy chips. Leading-edge chips get the headlines. Those are the smallest nodes, the highest performance, the chips used for top-tier AI and consumer devices. But legacy chips, older node technologies, are used everywhere. Cars, industrial controls, home appliances, medical devices, and critical infrastructure. Many supply chain crises have not been caused by a shortage of the most advanced chips, but by shortages of these legacy components. That means a semiconductor strategy cannot focus only on the frontier. Resilience requires a stable supply of the boring chips too. Packaging is also becoming a strategic frontier. Traditionally, the big prestige was in shrinking transistor sizes. But now, advanced packaging stacking chips, linking them with high-bandwidth interconnects, and combining different chiplets can produce major performance gains. This changes the map of competition because packaging capabilities are distributed differently across regions, and because it creates new ways to assemble powerful systems, even when access to certain nodes is constrained. Now we can return to the core question. Why is this race defining geopolitics today? Because semiconductors sit at the intersection of three priorities: economic competitiveness, national security, and technological sovereignty. Economic competitiveness is straightforward. Countries want high-value industries. Chips are high-margin, high-skill, and spill over into innovation across the economy. If your country leads in semiconductors, you have an advantage in AI, robotics, advanced manufacturing, and digital infrastructure. If you fall behind, you may become dependent on foreign technology in critical sectors. National security is equally clear. Modern militaries rely on advanced electronics, precision weapons, secure communications, radar, satellites, and cyber capabilities all depend on semiconductors. If access to chips is uncertain, military modernization is affected. That's why defense planners increasingly treat semiconductor supply chains as part of national security planning. Technological sovereignty is the hardest to define, but the idea is simple. A state wants the ability to make key technological decisions without being coerced. If your supply chain can be cut off, you can be pressured. If your industry depends on foreign components, your strategic options shrink. This logic drives both China's push for domestic capacity and the US and allied push for resilient, allied-based supply chains. So where do key companies fit into this story? TSMC represents the apex of advanced foundry manufacturing. Its value is not only in output, but in the ecosystem it anchors: talent, supply chain, relationships, and process expertise that are difficult to replicate. Samsung is crucial both in memory and advanced manufacturing, making it central to global computing capacity. Intel historically symbolized US manufacturing strength and is now a strategic focus for expanding domestic and allied fabrication options. Meanwhile, equipment suppliers and materials providers, often less famous, can be just as geopolitically important, because without them, even the best chip designs cannot be manufactured. This also explains why the semiconductor race is not simply US versus China or Taiwan versus everyone. It is a network of dependencies. The US depends on Asian manufacturing capacity. Taiwan depends on global equipment and customers. Europe and Japan depend on global demand for their specialized tools and materials. And nearly everyone depends on stable shipping routes, energy supply, and political stability in key regions. What happens next depends on how this network evolves. One possible direction is diversification. More fabs in more countries, more redundancy, and a more resilient supply chain. Another direction is fragmentation, competing technology blocks with different standards, restricted flows, and parallel ecosystems. The world could also see a hybrid outcome: diversified production among allies, but more barriers across geopolitical rivals. The Taiwan question remains the single most sensitive issue. The global system is trying to reduce the risk of catastrophic disruption by expanding capacity elsewhere, but it cannot replace Taiwan's role overnight. That creates a strategic incentive for many actors to preserve stability, avoid escalation, and keep trade flowing even while competing intensely in other areas. In the end, the semiconductor race is not just about chips, it's about who controls the foundations of modern power. In the 20th century, that foundation was often energy. The 21st century, it is increasingly computation. Computation runs on semiconductors. That's why microchips are the new oil, not because the analogy is perfect, but because the strategic logic is similar. Control the choke points, secure the supply, protect the infrastructure, and you shape the balance of power. If this video helped you understand the world a little better, give it a like and consider subscribing to World Explained. Your support allows us to keep creating clear and neutral analyses of complex global issues. Thanks for watching, and see you next time.